In this video, let's look at simply at linear regression, and we will start with simple linear regression actually. So let's start where we left with our little data set that is made of random variables. Remember, we created that table, that correlation table, and we could see that some variables are correlated. That was strange because it's random variables, they should not be correlated, but by chance some of them are. And we looked at random 5, rand 5 versus rand 4. We drew a scatter plot and made the trend line appear on the scatter plot. Okay, that trend line is basically the result of a regression analysis, and we have the result here with the equation of the trend line. That's a regression analysis result, basically, with the equation of the line and the R square. Okay, since we had only two variables, well, that's a simple regression analysis. We could have multiple regression analysis if there were several variables in the model. There's only one here, only two variables, the y and the x being rand 4 and y being rand 5. Okay, so let's look at regression analysis to find those things that, as I told you, is actually the result of a regression analysis. Okay, so I will push that on the side. Here we go. And what I'll do is actually go to the data analysis toolset again. And I will look, remember we were in correlation for that table. Let's go down and look for regression. And we open regression. Normally it appears with nothing in there. You can see that I basically already ran things to make sure that it would work. And let's run the regression analysis. The input y range, well, we said x5, rand 5 is our y, so we will highlight the column of rand 5, and for x we said rand 4 is our x, so we will highlight rand 4. Again, let's make sure that we click that there is a label. We just highlighted those columns with the label, so let's make sure that it is identified here. The output range, I could say that it's in a new worksheet or in a new workbook. Again, I want it in the same sheet, so I will just say make it appear below and on the right hand side of that cell. Okay, let's do that, and we click OK. Here we go, we have the result of our simple regression analysis. You see that sometimes you need to kind of edit the width of the columns because all the text is not displayed properly. But basically you have all your stats that are showing up here, and we can see that we know already some of those numbers. Actually, when there are only two variables, the regression analysis is very close to the correlation analysis. Number one, remember that correlation coefficient that we had found between rand 5 and rand 4? Well, look at the R. It's called multiple R, but generally we call it just R, and the Pearson R. Look at that, it's exactly the same value. Okay, that's normal. The correlation between two variables will correspond to the R value of a regression analysis when there are only one x and one y variable. Okay, and remember that we had an R square for that analysis, the fit of the model, R square. Okay, well, when again simple regression analysis, only two variables, well, R square is actually R multiplied by itself. If I were to do that, equal R times R, you see, that's what R square is. That's the square of R. Yeah, it's well named. So we have R square. Okay, that's what we had here on the graph. Okay, I told you that on that graph the trend line and its associated R square were the result of a simple regression analysis, and so here we have those numbers. What else do we have here? Let's look at the different numbers below that. We have a level of significance that shows that the model is significant. Okay, we generally want the significance to be below 0.05. Here we have 0.005, so we are kind of significant. But if we look at the details of the model, we have our coefficients. So 0.63, that's the number we had found here, all right, and 0.0518, that's the number we have here, 19, yeah, that's 19 because it's 57 behind it, okay. So we can see all the elements we had found on the graph is picked from the regression analysis. You can see that the p-values of those terms are, for one of them, is significant. So you can see that we have the same significance here and here. The intercept, though, is not so significant. So we have a problem with the intercept not being significant in that model. So normally, in the model, if we were to predict another rand 4 value based on the equation, based on the model, we would have trouble trusting the intercept. Okay, so maybe we would use only the coefficient for associated with rand 4. So basically 0.6337 times x, but no addition of the intercept. But you can see that the intercept is very small, so it would not change many things. Okay. But basically, normally you look at the p-value here to see if things are, if the model is fit or not. Okay, if the different elements of the model are fit or not. That's the fitness of the model. All right, so that's a simple regression analysis. We had only 2 variables. Well, we do exactly the same thing if we had several variables. So of course it will not correspond to a graph anymore because the graph is necessarily only for 2 variables, but it's the same idea that basically we will make a regression to try to find the best fit between the independent variable and the dependent variable. Y being the dependent variable, in our case that was rand 5, we want to look at things that explain rand 5. In that case we looked only at rand 4 as an explanatory variable for rand 5 as a dependent variable, as an independent variable, sorry. Okay. So Brad probably explained in more details in his class the regression analysis, but I wanted to show you a little bit how it works in Excel. So now we have that simple regression analysis. Let's look at how it works with multiple regression analysis, and you will see that it's basically the same thing. Okay, let's delete that. Shift cell left, yeah, that's fine. And let's reopen the data analysis toolbox. So our y, rand 5, that's the dependent variable or dependent variable. That's the one we want to try to explain, and we will say that the other variables will explain rand 5. And let's pick all the other variables, at least rand 1 to rand 4. We will exclude rand 6 just because it's not appropriately displayed for us. If I had put it on the left hand side, it would have been easier. But let's just take rand 1 to rand 4. Again, we have labels. Yes, I want the input in H11. Okay. And you can see that now, instead of having just y times a coefficient times x plus the intercept, I will have y times a coefficient times x1 plus a coefficient times x2 plus the intercept. Okay. And you can see that my r is way higher. Okay. My r square way higher. So again, it's weird that we find such an explanatory power inside random numbers that are not supposed to be connected to each other. But basically we have a much higher r square. But by the way, something that we need to worry about is that if you add variables to a model, you always increase your r square. So if I find an r square to predict rand 5 of, what was it, 0.27, whatever variable I add to the model will increase that R square. That's systematic. Okay, you always have some explanatory power in any variable, just because of chance. So you always increase your R square. That's why we invented the adjusted R square statistics. That basically is the same thing as R square, except that we take into account the number of variables that we put in the model. All right. So we compensate the idea that mechanically there's an increase in R square, but basically, is it worth having a more complex model to have very little additional explanatory power? So here our adjusted R square is still quite good, 0.4. On the previous model it was 0.24, I think. Okay, so a lot of people look at that to compare models to see if actually adding variables to a model is really useful or not. Okay, but we have our R square here. You can see that none of those values are correlations here, because basically in that table the correlation are calculated when one variable is looked with regard to the other variable. Okay, in those correlation we do not care whether that variable rand4 is impacted by other variables. We just look at rand5 and rand4. When we make the multiple regression analysis, we try to isolate the impact of each variable on the dependent variable independently, okay, in the model. So we can see that rand4 has now a very high coefficient, 0.75 here, as an impact on rand5. It has a good p-value here. We have rand1 that also has a high p-value. The intercept is more credible this time. Although it's not below 0.05, it is sometimes acceptable to go with 0.1 as the threshold. So, well, it depends on what you want to do, if you want to include that in your intercept or in your equation or not. So you run that model, you can see your R square, so the percentage of the variance that is explained in the model, how fit the model is. The model seems to be pretty fit overall, but when you look at it, it's actually, the intercept has some power, rand1 has some power, rand4 has some power, and then you can write your equation. Basically, it's y equal 0.42 times x1, let's say that's the variable for rand1, plus 0.75 times x4, the variable for rand4, and minus 0.34, the intercept. Okay, that would be our equation. One thing we can do, since we rand2 and rand3 are not supposed to be statistically significant, let's exclude it from the analysis. So to do that, I will put the two columns together first. Let's do that. Cut. Insert cut cell. Okay. Let's put it in front of run for insert cut cell. Here we go. And let's run the data analysis regression tool. Input range. Yes, that's what I want. Out and X range. That will be this one, only with rand1 and rand4 this time. Okay. H33 to put my output. That's what I want. Okay. I selected it twice. Here we go. We have another model, and you can see that R square has decreased a little bit because I excluded some variables. So in one direction, if I add variables, R square increases mechanically. Of course, if I take some off, R square decreases mechanically as well. But look at it. The adjusted R square used to be 0.42, let's say, is 0.44 now, because basically I don't have variables that pollute my model. And my model is significant overall. Okay. And here are my coefficients. You can see that they are slightly different from before. It's not 0.75 anymore, but 0.77. It's 0.46 instead of 0.42, and instead of minus 0.34, it's minus 0.27. And by the way, again, my intercept is not so reliable, so maybe I want to exclude it from my model if I want to make a prediction. It depends on the p-value I want to respect. Okay, so that's how you lead a multiple regression analysis in Excel, and that's how you interpret the outputs. And basically you can predict things based on several independent variables or several variables that help you predict the third, here in our case, the third variable, the dependent variable.